and PDE, then I have a choice to make. And both methods are totally legitimate, and for different applications and different orders of accuracy and so on, you might choose one or the other. But basically, you have two variables that you can differentiate in, right? Time and space. Yeah, I'm going to be very concrete here. Now, obviously, the PDE and mathematics people don't actually care if it's time and space or not, but this is good enough for us. And you can either treat time separately from space and try to apply what we've already talked about to the spatial variables and then something special for time, or you can just discretize the whole pile of derivatives all at the same time and see what comes out. And that's the difference between a semi-discrete algorithm and a fully discrete algorithm, at least in the language of your textbook. Right, so let's think about the heat equation as a semi-discrete object. So remember, hopefully I got the sign right. I always get this stuff wrong. I think it's right. So remember the heat equation in one variable is pretty simple. So our unknown here is a function of time, f of time, and of position. Right? And the idea is that this thing gives me at any time t some distribution of heat along some part of the real line. Right? And so as time moves forward, the heat kind of diffuses outward until eventually it reaches just a boring steady state. Yeah? So let's say that I want to solve the heat equation and do it in a semi-discrete fashion. Then what does that mean exactly? Well, what I can do is discretize the x variable only. So we're going to think of the heat as still a continuous function of time, but now I'm only going to sample that continuous function of time at a discrete set of spatial points. Yeah? So if I do that, right, then now what happens? Well, you can think of f, so let's say that I have, again, n plus 1 sample points, right? Then you can think of your discretized in space version of f as taking in a value for time and giving back these n plus 1 samples in space of the heat at each of these different positions. Yeah? Now, why might I want to do that? I'll tell you why. And that's because for two reasons. For one thing, right, this matrix L we've already written down, right? This L is our favorite, 1 minus 2, 1, 1 minus 2, 1 matrix that we keep using, right? He's the second derivative matrix. Yeah? That's reason one. And so if we discretize in the space variable only, we get what? We get an ordinary differential equation that comes out on the right-hand side. This makes sense because now I've replaced the continuous stuff in space with something discrete. Right? Remember, ordinary differential equations are all about one continuous variable and a bunch of discrete outputs. Yeah? So what can I do to solve the semi-discrete heat equation? Well, it's actually pretty simple. I can just apply the methods that we talked about last week, or 2 weeks ago, right? We already learned all about how to solve ODEs, right? Things where you only have one variable you have to worry about, is time one. And so you can just use them out of the box. Everything from forward Euler, backward Euler, RK3, RG3, whatever, all apply here, and so do all the stability conditions and so on. And this is why this is a very attractive option, because somehow the theory of ODE is very well understood, and we'd like to make all of our theory talk to that. Yeah? In addition, there's a couple nice things that happen in the particular case of a semi-discrete PDE. So, right. So remember that a parabolic PDE kind of looks, it looks elliptic in all the variables except for time. Right? Your matrix is positive semi-definite, and the semi part comes because the time variable only has one derivative instead of two. But all the rest of the derivatives are kind of happy and elliptic, positive definite, whatever. Yeah? So we already showed that this matrix L is negative definite. Yeah? Nothing has changed. It's the same matrix. So in particular, that means he has all negative eigenvalues. Yeah? Now, and since it's symmetric by the special theorem, so we're going to use all of our review words today, by the special theorem we know that he has a full set of eigenvalues and eigenvectors. Yeah? So let's say that I knew it's f bar of 0. That is, I know the distribution of heat at time 0. And let's say that I write it in terms of the eigenvectors of this matrix L. Yeah? Well, then if we recall from several weeks ago, we actually already worked out in closed form what the solution to this, this exact ODE is, right? It's nothing more than the sum over I of AI e to the lambda I t times vi, I think. Yeah? And in particular, I just showed you that this matrix is negative definite. So what happens as time goes to infinity? All of these terms just die. Yeah? So this is a really nice property of a semi-discrete, this is a lot of words, a semi-discrete discretization of a parabolic PDE. Hopefully that parses now, except for the gentleman that just walked in. And the basic idea here is that even though I just made an approximation, right? I approximated the spatial variables with this sample thing, you know? It still has a very nice sort of heat diffusive looking behavior as a semi-discrete equation where t is continuous. Yeah? Because all of these terms just vanish and go to 0. There's no crazy oscillation, nothing, which you wouldn't expect in heat diffusion. Yeah? So that's kind of a nice property about semi-discrete stuff. Yes, Catherine?
Oh yeah, so you're saying that we're approximating XX
Yeah.
with LF,
Mm-hmm.
and LF is negative definite
Yes.
because it's elliptic.
What was that?
Because it's elliptic?
Yes. Yeah.
Okay.
I'm a little bit glib about negative versus positive definite. Just think of definite equals easy. Yeah, that's what really matters here. And you should do your homework and look at your particular matrix and check whether it's positive or negative. If you want to be technical about it, it's because the adjoint of the first derivative is minus the first derivative. Be a little careful about it. Anyway. Okay, so that aside, we can solve a semi-discrete system. We only have one continuous variable now, and that's time. And we can solve it using these time-stepping strategies we talked about 2 weeks ago. By the way, hopefully you guys know, I think I used the word time-stepping without actually defining it explicitly. The idea of time-stepping is you know a function at time 0, and we don't know this function continuously, but we can think of it in like discrete steps, right? So we call it time-stepping. And we have all these different strategies for this. We have forward Euler, backward Euler, RK3, whatever, trapezoid, and so on. And I strongly encourage you to try problem 1 on homework 8 to review all of these. Yeah? If you can't implement problem 1 on homework 8, then there's a misunderstanding that you should fix, because it's actually pretty straightforward. Right, and so we can use machinery that we already have, including all of our favorite stability bounds and so on. Right? One interesting question here is what time-stepping tool should you use? And there's no clear answer. One thing that you'll notice if you do homework 8 is that implicit solvers, like backward Euler, tend to dampen energy in a system. Remember that backward Euler is unconditionally stable. So even if I'm simulating like a wild and crazy system of springs zipping around every which way, I still can't make backward Euler die. Yeah? And this is a nice property in that my simulation will never explode, but the way that backward Euler accomplishes this is by dampening out energy. Right? So in fact, if you're trying to simulate the wave equation using backward Euler, you can run into some trouble because waves like to just propagate back and forth, but if you don't run it over enough time, your wave will just get bored and stop using backward Euler. Forward Euler, of course, has time step restrictions and so on, but it does preserve a little bit more of this wild and crazy movement. And if you do your homework, you'll play with 1/3 class of integrator, which is called a symplectic integrator. This is a little bit of an advanced topic, but basically it has energy preservation properties that make sure that it doesn't go too wild and crazy or diffuse energy all at the same time. But at the cost of being a little bit more expensive or hard to evaluate and so on. Yeah? This is a big engineering issue. There's no clear answer, and usually you should experiment with a couple if you have the possibility. All right. And alternatively, one thing you could do would be to decompose f at time 0 in terms of the eigenvectors of L, and then just use this formula here and not use any time stepping at all. This sounds like an attractive solution, right? It just obliterates the need for what we did 2 weeks ago. But on the flip side, it requires that you compute all the eigenvectors of L, which can be a very expensive process, right? Because even if L is sparse, his eigenvectors may not be. And but this is actually very common, especially in areas like what I do in geometry, because if you look at the Laplacian, it turns out that the eigenvectors have to do with resonant frequencies of your domain. And so one thing you can do is say, I only want the first couple eigenvectors, and those will cover or span the low frequency functions, and maybe that's good enough. Right? So I want kind of a low frequency approximation of my ODE, then I can get that in a pretty inexpensive way. Right? So the other option, which we're not going to cover a whole lot of, is the idea of a fully discrete PDE. And this just says, basically, we're going to go back to how we solved elliptic equations. Remember, we discretized the derivative in the x variable and then just solved the big linear system. In fact, well, we could discretize x and t and just put finite differences every which way and then solve a giant linear system. And that's, in fact, what a fully discrete method does. Fully discrete methods can be quite large. Generally, what you'll have happen is you'll write a fully discrete method, and then oftentimes it'll actually end up looking like time stepping anyway, because it's very difficult to couple time 1 and time n in any intelligent way. But you do have to be a little bit careful. And you also have to be very careful in these schemes that they are convergent and consistent and all of that kind of stuff. And there's a very well worked out theory. There's a phrase that you'll hear called CFL conditions, which are all about making sure your discretization is well behaved. One small philosophical point is what the heck does fully discrete mean? Because in the end, if you do a semi-discrete thing, you still have to discretize time eventually when you use your time stepping tool. To me, this distinction is not all that exciting. But usually when you hear the phrase semi-discrete, what it means is that you've kind of done this in 2 steps, and fully discrete means you derived it in 1. Not a big deal. Okay. So in like 15 or 20 minutes, I thought we'd go over 2 examples of PDE solves that you might see in practice as both kind of for fun and to convince you that this isn't just totally theoretical. And in fact, both of these are pretty recent developments in computer graphics, image processing, and so on. So the first, if you open up your web browser and you Google for gradient domain, you'll notice this is a very trendy topic in image processing. Right? And the basic idea here is that oftentimes, so like, if you were to think of writing MS Paint or Photoshop or whatever, you'd probably think about manipulating colors and pixels in an image. Right? But sometimes it actually is easier to manipulate the gradient of your image. And this is a little bit weird. It was actually a very smart observation that people made about 10 years ago. And since then has led to this like combinatorial explosion of research papers, because that's what we do. But anyway, as a concrete example, let's say that I wanted to solve the problem of inpainting. I think this image probably shows you everything you need to know about inpainting, but the basic idea here is that maybe I have some background image, like this water here, yeah? And I'd like to paste onto this water 2 children and a bear. I'm not sure why, but you know, this is part of my horror film, and although the bear and the children here seem to be kind of in harmony, and I'd like to do this in a natural way, but the problem is that the lighting and the other conditions in these 3 photographs is completely different. Right? That's, you can see the kids are in like a light blue pool, the bear presumably is in a lake, and hopefully not in a pool, and who knows what the third thing is. Yeah? But we'd like to paste them all together in a natural way. So the key observation of gradient domain image processing, at least for inpainting, is that even if the absolute values of pixel colors are not so good to just paste on top like you see on the left here, right? The gradient still is all right, in the sense that what really matters is that the bear is darker than the water, right? And that the children's faces maybe are lighter than what's around them, and so on, right? And that's a gradient relationship, right? What it's saying is that the slope of the image colors changes as a function as you move along the image. Does that make sense? Like the pixels on the boundary of the bear pixels are darker than the not bear pixels, and so you have a big gradient there. Yeah? So what gradient domain inpainting does is it says, well, rather than just pasting colors, I'm going to paste gradients and then reconstruct the image. And in fact, it's a very effective method for inpainting. Yeah? So here's the general pipeline here. So we're going to think of an image as just a continuous function of x and y. Yeah, so you remember we had these children and the bear, and so for each point on the image plane, that's just some color, RGB. Yeah. Well, the first thing I'll do is compute the gradient of the image. Now, what is the gradient? That's nothing more than the first derivative. Yeah, we have lots of ways of doing that. So, for example, let's say that we think of our image as a grid of numbers here. is actually kind of a cool example. I like this shape. Right, so you have, yeah. So what can I do to compute the gradient? Well, the x derivative is gotten by subtracting that way, and the y derivative, depending on which direction you like y, is something like that, right? And so you can think of these derivatives as sitting at the centers of the pixels, or between, yeah? So now for each pixel, or each, sub-pixel or whatever, it turns out actually this distinction doesn't matter a whole lot in this case, because images have a lot of pixels. You now have some vector which is pointing in the direction that the intensity is changing the most, right? You just took the gradient of the image as a function of x and y. Yeah? Think of your image as black and white, otherwise the gradient is kind of hard to think about. Yeah? So again, like if you're at the border between the bear and the water, where is the gradient of the image going to point? It's going to point toward the water, right? Because the bear is dark and the water is light. Yeah? So now I compute the gradient as a vector field, and I'm going to edit this gradient vector field. So in particular, let's say I compute the bear, the gradient of the bear photograph and the gradient of the water photograph. And now what I'm going to do is replace all of the gradients in the little bear part of the composite image here, right? Like in this little piece. I'm going to take all the bear derivatives and just drop them in there, right? So I'm going to have water derivatives out here, kid derivatives in these two slots, and bear derivatives up there. And I'm just going to smash them in. And then I'm going to go back, well, in the end I don't want a gradient field, I actually want an image, so I have to reconstruct. So we have to find a function, g, right, this will be our new image, such that his gradient equals this new edited thing. Do you see the pipeline here? Take the gradient, add the gradients, undo. No? Pretty simple. Now, there's a question, and actually, it's one of those questions that looks kind of innocent, but then turns out to be like the topic of like several textbooks. Right? And that is, are all vector fields, even just on an image, are all vector fields on an image the gradient of a function? The answer is no. There are more vector fields than there are gradients. Yeah? In particular, things with lots of curl don't have gradients, which makes sense, right? Because think about what this would mean, right? If I had a vector field that looks like this, right? This says that and this where the gradient of something, that means that the function is increasing this way, increasing this way, increasing this way, and so on. So if I drew a loop in this image, it effectively says the value here and the value here, it doesn't match up, right? So in fact, gradient vector fields cannot have curl. Yeah? If it turns out this is a topological fact about the image plane. You can have gradient vector fields on donuts that have very different behavior, but we'll discuss that another day. Yes?
Does that matter when you're reconstructing the image? Because you only did a one-way gradient from the original image to V, and then you modify V, and then you solve for G.
Yeah.
But so does that matter?
Well, since I modified V, I no longer have any guarantee that this new modified thing is the gradient of anything equal. In particular, what will happen is, let's say that I have the photograph like this, and I've pasted the bear in the middle. And then right around the boundary of this thing, there might be some kind of inconsistency. Yeah. So but we still want to reconstruct it. We kind of suspect that even if we pasted this thing in from two different images, so it's going to look pretty close to something that's a gradient of an image. Yeah. Well, what do you think we're going to do? We only have one trick in CS205A, and that is solve a least squares problem. Yeah. So if we want to do this, we can say, okay, our unknown is a function g. So we're going to take his gradient, subtract out the vector field we want, square it, and integrate. Yeah? Same thing that we did last lecture, same thing that we did 2 weeks ago, same thing we did in week 2. Yeah? We're going to solve a least squares problem over all functions g. And if you recall, this is actually quite close to the Laplace equation that we talked about last class. Remember, the only difference is that one v was 0. Right? We just minimized the gradient of the function. And now I'd say, I don't want the gradient to just be 0, I want it to match some function v. Yeah? And it turns out that if you parallel the proof that we did last time, which I encourage you to do at home, it's almost exactly the same, you get a Poisson equation instead of a, whatever the heck, a Laplace equation, right? Where now you say the Laplacian of this unknown function g is equal to the divergence of v prime. Yeah? Remember, the v prime is known. V prime is the thing that we edited. So what do? We compute its divergence, right? Remember, the divergence is what? It's just the sum of the first derivatives in all different directions. So that's something I can discretize on this grid pretty easily, right, just by subtracting in different directions. I compute the divergence of G, or of V prime, and then I just invert this operator delta squared, or whatever, Nabla squared. Yeah? This is an elliptic operator, once again. Remember, there is a negative definite matrix, once again, and so we can use conjugate gradients, we can use preconditioning, we can use Cholesky, whatever you like. Yeah? And so this actually, is just this little amount of machinery that we covered in the last 2 lectures is enough to get you a very powerful image processing tool. And if you're bored on Google, you should definitely Google for gradient domain image processing, and you'll see some really, really impressive results that people can get with this trick. In fact, another trick that people do, there's a piece of software that came out a few years ago called Gradient Shop, and basically it's the Photoshop for gradient domain stuff, and people will paint using gradients rather than using colors, which apparently, I'm not an artist, but apparently you kind of get used to it after a while, right? Obviously your brain probably thinks in colors and not gradients. But the artists are able to get these really nice, smooth looking, very cool effects because that's what gradients are all about, right? They're changing in slope instead of color. Very neat. Okay. So, about 2/3 of this class has asked me if we're going to cover fluid simulation, so I felt obligated to mention it at least a little bit. I should warn you guys that I am not a fluid simulation expert by any means. So I did some reading of my own, and we're going to try and talk about how fluid simulation relates to some methods that we talked about in CS205A. But just as we already know that the Navier-Stokes equations are rather complicated, their discretizations are also very complicated. But anyway, so that aside, I'll attempt to guide you through my understanding of what's going on and answer any questions you have. Right, so if you recall from our last lecture, we can understand the dynamics of a fluid, right? You can think of a fluid as, at least like inside of a jug, as a bunch of pressures and densities and so on, forces, right? And they're all governed by this one big giant PDE called the Navier-Stokes equations, which show how all of these different quantities are coupled together in a nice way. And an incompressible fluid means that you can't like fill a balloon with your fluid and just kind of smush it down, which is the case for things like water, things like air you have to be a little more careful with. Yeah. So there are lots of different discretizations for fluid flow, and generally they fall into 2 big patterns. This is actually the case in theoretical PDE II, which is something I'm more familiar with. But right, usually the 2 big vocabulary words for an area like this, again, if I were to go through the last lecture and look for extra credit questions or something, these would be the sorts of things I think about, are whether a discretization of something like the Navier-Stokes equation is Lagrangian or Eulerian. How many of us have heard of this distinction before? So you guys probably would know more than I do. Right. So the idea is this. If I have a big fish tank full of water and it's swishing around, right, then there are 2 ways to think about this water. One of them is that you can think about the water as this big collection of molecules that are moving around according to Newton's laws and so on. Right? They're all interacting and swishing and moving around inside of this velocity field. Right? And so a Lagrangian discretization of fluid flow basically does exactly that. It thinks of water as this big collection of particles, and it tracks the particles as they move around. And oftentimes Lagrangian simulations look an awful lot like what we've already covered in this class. It's just that the forces between these particles are a little bit weird. Yeah? So if you look at things like smoothed particle hydrodynamics, SPH, this is a very common method that is Lagrangian in nature and is very, very important for, especially for real-time fluids. If you want to have like water splashing around in your video game, then you might use SPH to see other particles. Contrastingly, an Eulerian fluid says that we can kind of change our reference point in physics, right? You can either track the water as it moves around, or I can say, I'm going to stand at this point in my fish tank and watch water go past me. Right? And so you can think of, okay, the velocity of the water as a function of time in 2 ways. Either the velocity of the water particle as he's moving around, or the velocity observed as I stand at this point. Right? For example, maybe I have like one of these wind collectors and I collect the wind motion and at different weather stations. That would be an example of an Eulerian discretization. Right? So Eulerian things tend to live on grids, Lagrangian things tend to track particles around. Right, so a very common example. I thought I would show you guys this picture just because it's quite similar to the story that we have talked about. I'm an elliptic PDE guy, by the way. And basically what people do in this field is they take different quantities, for example, the density, the pressure, and the velocity, which has u and v components, and they put them in the places that make sense. Right? So certain numbers will live on the edges of a cell, certain will live in the center, and so on. And then what will happen is you differentiate, right? You take these finite differences, the midpoint of your finite difference is going to tell you where the next object is. Right? And so actually the discretizations of this are quite simple, and I've included some links in the lecture slides to discussions of this, although we obviously don't have time to cover a lot of it. So the typical approach in incompressible flow is to take that one equation, Navier-Stokes, and split him into several, right? So, and they can, one form of them is here. And this is called a splitting. The idea is you can write down lots of different properties of your velocities and pressures and so on, and that all couple them together, and these hold if and only if that one slick Navier-Stokes equation holds. But these ones are a little bit more physical. Yeah? So for example, the first one says that your velocity field, which is u here, is divergence-free, meaning that you can't just take a fluid and kind of stretch him out. Right? This has to do with your incompressibility. Yeah? And then the second and third are advection equations. And advection is all about, if I have a velocity field for my fluid, right, it tells me how things are actually moving in that velocity field. So let's say that I have, I know the direct, this is kind of like, yeah, I have a bunch of velocities of my particles in a nice Eulerian way. Right? They're all sitting on a grid. And I want to track the particles as they move around. Right? That's called advection. Yeah? Just like, advection and convection for like your GE oven. Yeah? So, right, so the steps for flow, unfortunately we're low on time, which is good, because I'm if you want to solve a fluid flow equation, it's actually quite simple to implement using all the tools that we've developed in this class, right? So first, you say, well, this is sort of an ODE problem, and that you have a time variable, and what you can do is look at the dynamics and the velocities you see in space, and choose a time step delta t that you know is going to be stable and consistent. This is particularly important for fluid simulation because depending on whether your fluid is crashing around or splashing or settled or so on, you might have to adjust your time step to resolve that behavior. And that's a very important decision. Beyond that, you have to advect your velocity and apply forces, which we'll return to in the next slide. And it turns out that your pressure solve is nothing more than elliptic PDE in the rest of the variables, which we've already covered. Yeah, and then you just repeat. So it's actually it's not too complicated in the end. Basically, instead of having one equation like the ODEs we covered, we have three, and you just kind of iterate between all three of these guys, right? You project your divergence out, and so on. Yeah. It's obviously a very high-level view, and I'm probably getting lots of things. So, right, one really interesting idea that I do think is worth talking about a little bit is how do you do that advection step? This is actually quite interesting. So if I have a grid of values, conveniently I've already drawn a grid here. Let me extend it a little bit. And in each cell I have a velocity of how stuff is moving. Yeah? And maybe in each cell now I have a pressure at time 0 and I want to know the pressure at time 1, given that they're moving along in this vector field. Right? Then that is an advection problem. Yeah? And so there are lots of ways to discretize this. You could try and discretize the actual advection equation and then use one of our ODE time-stepping things, but it turns out this can be an unstable operation. These matrices don't have nice eigenvectors and eigenvalues and so on. So a very popular option is to use something called semi-Lagrangian advection. So remember, our Eulerian fluid is going to have one number per cell that tells us the density of the fluid and the velocity and so on. Right? And I want to know the density at time 1. Well, the way that I can do that, well, I could think of there being some particle of mass m here, which is proportional to the density. Right? So I have the velocity at time 0. Well, I could use forward Euler and kind of stick that m over here somewhere, right? And then sum up. But there's a problem, which is that I might have two different vectors that point like up here and down there, and then this cell doesn't receive any mass. Right? This is an issue. So in semi-Lagrangian advection, this is actually a very clever trick. All I say is, instead of doing that, we're going to look backward in time, at time 1, and go this way. So to figure out the mass that should be in this cell at time 1, I'll look along the vector field here, backward in time, and then use one of the interpolation tricks that we've covered in previous lectures to guess what the density should be at that point. Yeah, it's kind of a clever trick. You have to be a little careful though, because your velocity field is still at time 0 potentially. Right? So you look backward along this thing, and then what you hope is that the velocity field over here points back toward where you are, but that might not happen. So more advanced methods will update your guess of this point. So anyway, actually fluid simulation isn't so bad, right? You update your pressures using an elliptic one of these elliptic solves, which is something we've covered in detail here. And then you would vect velocities and you would vect densities and you repeat. Obviously it gets much more complicated when your fluid has a surface, for example. So simulating smoke, I think generally is a little bit easier than doing water where it's splashing around under surface tension and so on. Right. So anyway, that's all we'll say about that. So a high-level view, that actually used to be the topic of CS 205B, but that class no longer is with us. However, there are classes in the CME department and in Aeroastro that cover this in more detail. Right. Oops. So, we've got about 10 minutes left, and I thought it would be useful just to wrap up this class just a little bit, and before I send you on your way and get you studying for your final. So, right. CS 205A covers a stupid amount of things. We have done so much in this quarter, and hopefully you've at least got a sort of a high-level view of a lot of different numerical methods that are applicable to computer science problems. So I thought it would be useful to kind of walk through the story just a little bit, highlight the aspects that I think are important for you guys to know, especially for life, but also on your final, and just remind you a little bit of where we've gone and how the story, while it was very fast-moving, is actually pretty consistent. Yeah? So we began in this class by talking a little bit about how a computer actually would store a number and what it means to measure error and so on. And that was a theme for a lot of the calculations we did later on. And we have all kinds of sources of error that we've seen in 205. Right? We started out by saying, well, if I use IEEE floating point precision, then we already have some error induced just because I'm rounding and I can't represent every number. But then later on, although we didn't know it at the time, when we did things like quadrature and interpolation and differentiation, we had this other kind of bizarre error called truncation. Right? Where the idea was maybe I write down a Taylor series for something and I cut off higher order terms. And something that's important to keep in your mind is sort of what the hierarchy is of different sources of error. Right? So obviously truncation errors generally are larger mistakes than the little end bits that get rounded off in IEEE precision. And in fact, there's an even larger source of error that occurs in most places, which is the fact that your model might not be that accurate. Right? So if I'm solving the heat equation, and my heat at time 0 that I provide as input to my discretization of the heat equation is inaccurate, then that error might trump all the rest of the error that I see, whether it's from truncation, discretization, anything else. Yeah? And that's something that's very important to keep in mind. In this class, we didn't have time to implement every single method that we covered. But in general, it's very tempting to always use the highest order approximation of assorted quantities. And sometimes that's actually not only unnecessary, but actually bad, because those are very sensitive to noise, and if you have a low order input, there's no reason for a high order method. Yeah? So a good example of this is when we have these discretizations of the derivative of a function. Right? Remember that like our divided differences just as first order accurate, but then we can do this centered difference thing and it kind of looks more accurate. But then somehow the centered difference is actually not so great for solving PDEs because of the fence post problem. So you always, when you have a higher order approximation, you have to be very careful to justify why you're using it. Yeah? So anyway, we moved on from there to basically the whole first half of this class was about linear algebra, and the theme that you should keep in the back of